Okay, I think we are alive. Hi, everyone. Welcome to those who are who attended the first lecture. Welcome to the new attendees also. Can you see my slide? Okay, cool. Google has been playing today. I think they're having some issues with their infrastructure. So hopefully it won't affect us. So let me just check the chat again. So the slide is well visible. You can all see it. Okay, cool. Thank you. Okay, so welcome to this welcome to this session, the second session. This time about group theory. So it will be again a kind of kindergarten type of session, but nevertheless, I hope some of the stuff will be interesting. Before we jump in, I will just go through quickly the foundation module stuff to update you on one thing. For those who are just who are attending the live session for the first time, so last week we covered set theory. That's why the thing is in green. So hopefully we will you will be in this journey with us to cover everything green. So today we are covering group theory, and it will be a kind of easy, gentle intro. Not the least, this is abstract algebra. So one has to be very careful because I don't want to lose anybody. So we'd rather start very from the very basics. Because in the end, the reason we are having group theory today is because we took this approach of layering structures on top of each other. So last week we started with sets. Today we are adding something on sets. In this case is the structure of group. And then next week we will add a structure of ring and then fields. So naturally you need to know what a group is. And this lecture actually, all you need to know is actually what additive groups are, because that's what I need you to know in order to tell you what rings are before going to fields. So that's it, really. The other thing I wanted to say is I added an extra lecture here on the matrix groups. This is because in this session on group theory, we will leave a lot of stuff that we won't be covering. So instead, we'll do one session where we'll go through the important stuff that were left out today in a little bit more rigorous fashion. And then hopefully, before we arrive here, you will already be feeling comfortable with working with abstraction, especially in the algebraic sense. So just to let you know, there is an extra. It's optional. If you guys, because I will share some lecture notes, some curated materials, study materials. If some of you manage to extract some of these concepts from, by self-studying, you don't maybe need to attend the extra session on this before we jump into matrix groups. So yeah, let me just go back to the chat before we, can anyone see? Can you still see? I mean, the slides. Okay, cool. Thank you. Thank you, guys. Okay, so see if this thing clicks. Okay, so the agenda for today, we'll start first with defining binary operations on set. And then we'll go through the group axioms, which tells us what groups are. And then this is where the concreteness will start coming in. We're going to go through this notion of additive notation. I hope I spelled it correctly. If I haven't, apologies. And then we'll go and define complex additive matrix group. So today we already defined the notion of a matrix, in this case a column matrix. Normally this is done after, in standard textbooks you do this after you have gone through rings and fields, but we will do it because we are dealing with the complex numbers, and underlying them, they have already the structure of rings and fields, so we lose nothing. But next week, you will know what fields and rings mean. So it doesn't really make that much difference. If anything, it will only help you, in my point of view. I hope at the end of the session you will agree with me. And then we'll define 2 by 2 complex matrices. And then we will define a general linear group. This is a very interesting group in mathematics and also in physics. And then we will define the concept of action and concept of a commutator. This is not the commutator that some of you coming from physics are expecting. We might get closer next week when we define the concept of ring. But yeah, so this is the agenda, and then I will go through the study material stuff to make a comment on where you should focus and so on. Okay, so first definition. Let me first see. Does it help if you hard refresh your tab, Control Shift? Yeah, I hope so. Yeah, thank you for that. Try a different browser. Okay. Can you see my, can you see the slide? The binary operation slide? Yes, okay, yeah, sorry for that. Maybe next week I will try another browser if it helps. So anyway, so the first definition, before we define groups, we need to know what binary operations are in the mathematical sense. So given a set, a non-empty set, obviously, a binary operation is a prescription or an association that takes a relationship that takes 2 elements of a set X to generate a third element. We call that psi1 star psi2. So that's what the binary operation is on a set. Or a more formal way to define it, as stated there, is it's a map from the Cartesian product of a set to itself. Okay. Obviously, at this stage, it doesn't say anything about whether this binary operation is defined for the for all the elements of X, which is what we want. And so the next definition is exactly that. We say a binary operation star on X is closed if for any 2 elements psi1, psi2, the operation is defined and it takes psi1, psi star into an element of X. Okay. So given that, here's a very simple toy example. So given X equals N0, I hope you remember what N0 is, and star equals plus, which is the normal addition in N0. It's clear that plus, in this case, is closing N. Same with the multiplication. Okay, let me check the chat. Does anyone have any doubts about the definition of closed binary? Can you see why the plus operation is closed in N0? Is it understood? Yes, okay, cool. This is the last chance because after this, the train has left the station, so it will be very hard to go back to the station. Before I define the notion of groups. So, okay, so I assume okay, so Stefan is saying, so a closed binary operation, so it means that the operation is defined for any 2 elements of X. Okay, so for example, for N, for example, N0, if you take any two natural numbers, you add them, the result is another natural number, right? The same with the multiplication. If you take 2 natural numbers, you multiply them, the result is another natural number. Is it understood now? Okay, so maybe there is some latency with the screen. I hope everyone can see. We're still on the binary operations thing. Can you see the screen? Okay, so I assume now it's understood. It's clear what a binary operation on a closed binary operation. This is what we want for the definition of group. Nobody has any doubts about this. I can move on, right? Yes, okay, cool. Thank you. So now, here's the group, the definition of group. So a group is really just a pair composed of a set G, because it's a group, so we call it a group. We call it a G. The set is non-empty, obviously, and star is a closed binary operation, but it satisfies these axioms. So let me check again to see. Does anyone have any question? Yes, it necessary. Associativity is a requirement for a group. Yes. Yes. We will see next week for rings. You can relax this, and then you have like non-associative rings and these things. But that's the thing. But for groups, associativity is a requirement. If it's not, then it's not. If any of these conditions is not met, then set G is not a group. Okay. You will see in a minute. We will make this more concrete. At the moment, it's in the abstract form, in a mathematical fashion. That's why this is abstract algebra, right? Another important definition is a group is commutative or abelian if for all psi1, psi2 in G, you have psi1 star psi2 is the same as psi2 star psi1. So the order, in other words, it's commutative if the order by which you take the operation does not matter. It yields the same. On the other hand, if that's not the case, if there is even one single element, two elements that do not satisfy this, then the group is not. It's non-abelian group. Okay, to be abelian, it has to satisfy for any two elements of G. Okay, so I'll check the chat again. Yes, you can prove this. Yes, you will see later on the thing. Yeah, for groups. Yes. Okay. So here's the first proposition. So it says if G star is a group, then the following statements are true. The first is that the identity element in G is unique. So we cannot have two identities. So this means identity is a well-defined concept in G. The same with the inverse element, psi tilde. So I won't go through this thing because you will have the slides later to see the argumentation, and you will also see a version of this on the study materials. That this is the key to take the key to note is really that groups are this is the intrinsic property of a group, that the identity is unique, the inverse of its elements are unique. Okay, you will have this thing to read through the argumentation for you to be able to see this. Let me check this chat. Yes, Sohal, yes, thank you. Yeah, if you drop the associativity, yeah. No, this proposition is valid for any group. It doesn't matter if it's abelian. Any group, anything that we call group will have a unique identity, and it will have any of its elements will have unique inverses. Okay. Okay, so now, as you notice, I haven't given any examples of group yet, because I want to switch gears a bit into concreteness. If you attended last week, we have this diagram where we go abstract, concrete, just to make things easier, because, I got the survey that not many of you are, have been exposed to groups before, and there's a lot of you who don't also feel comfortable with abstraction, so I'm taking it very easy for the time being. Okay, so here's a very important convention. So whenever we deal with an abelian, a commutative group, we don't use star, we just use plus, and we call it an additive group. Okay. Another convention is the E element, we denote it 0, and the tilde, the inverse of psi, we call it minus psi instead of psi tilde. So therefore, I've rewritten for abelian groups. We can rewrite the group conditions. This is just for abelian groups. For the rest, you can because of this condition here, obviously commutativity, because it's abelian. So therefore, any abelian group using the additive notations will satisfy this. So this is the group notations. The thing you can see 0. So 0 plus psi, equals plus psi plus 0, blah blah blah, and so on. So this is, I assume this is already becoming familiar, right? You can see. And you see what could be a group from the sets that you were exposed last week. What could be a group? An abelian group, at least. Okay, I will help you. Let me go next. Can you still hear me, by the way? Because I didn't see anything on the chat. Oh, okay, cool. Okay, so let me help you with the example. So maybe this is too abstract still, but finger crossed the next slide will not be that abstract. There you go. Okay, so which of the following pairs form an additive group? Option 1, N0 plus. Let's go through that actually. Who thinks N0 plus is an additive group? Does anyone think the N0 is an additive group? Yes, fantastic. So that's true. N0 cannot, because if you look at the axioms here, I was very careful to put the axiom on the side, it fails, right? It fails because it doesn't have the inverse. It fails here in this axiom, So there isn't, because as who said before, was it Ryan? As Ryan said, you don't have the inverse, the negative numbers in this case, okay? So no inverses, so it doesn't. Whereas the others, Z, someone already said this, so Z, the set of integers, is a group, right? The same with reals, the same with C. So without this, all of them are all groups, okay? So does anyone have any issues with, seeing that N0 is not, cannot be a group because it fails in this condition of not having inverses? Okay, so I assume nobody has any doubts on this. That's perfect. Okay, cool. Thank you. I'm glad the examples are clear. I took a little bit of extra time to put this together to help it, because I know a lot of you are not used to these things. I wouldn't do this if it was a thing like for like an audience of undergrad math students, for instance. So what about this one? Z3, if you look at this table, you don't have to answer this now. You can, if you cannot see whether this is an additive group or not, First of all, does it have a, let's look at this action, for example, 0 happens to be 0, right? So 0 is 0 in there. You can also see the other axioms are also, so, what's the inverse of 1, for example? Oops, sorry. Yes, so it looks like an additive group, and it is. I can say you can go and double check this after, by going through the table, but it is an additive group. So this brings me to the next definition, the obvious one. So a group is finite if its underlying set is finite. So there you go. This is finite group, right? Because this is finite. It has 3 elements. You remember last week when we talked about cardinality. So this is infinite because its underlying set is infinite, right? So actually, sorry, the slides are playing again. In terms of infinite stuff, last week you learned that there is countable infinite, there is uncountable infinite. So Z a countably infinite, infinite group? Yes, it is. What about R? Okay, so Anne is saying no. So Anne, let's see if we can help Anne. So are you saying Z is not countably infinite, Anne? Okay, changes to yes, okay. What about R? Is R countably infinite or uncountably infinite? Yes, it's uncountably. Now, I didn't mention about C last week. What about C? Yes, R is uncountable. Yes, okay, yeah, so fantastic, well done. So it shows that you were listening last week and you went through the materials, huh? So that's good. So yeah, obviously, yeah, so this is true. R and C, obviously R is a subset of C, or another way to say that C has a copy of R, so therefore if R is uncountable, obviously, certainly the larger set is uncountable, right? So, okay. Another definition is that of a subgroup. We won't go much into it today. We will save this for the other module when we talk about matrix groups, but nevertheless, it will become handy for you guys to know this. So a subgroup is a subset of G where the subset is also a group. So in this case, H is a subgroup of G if H is also under the same binary operation. Huh? So it has to be under the same binary operation for H to be a subgroup of G. And one obvious thing is obviously G is a subgroup of itself. It's a subset of itself, and the binary operation they're generated. The same with the E. What about these ones? 2Z, which is the set of even numbers with addition. Who thinks that's a group? Yes, it is. It is a group. So, yeah, okay. And you can also see, what about 3Z? Z of all multiples of 3. You don't have to answer this the same, okay? This one is harder. Is every this one I won't say anything. I want you to go home and scratch your head, think about it, and then you can you might actually see this on the study material anyway. So, but before you look at it, just think about it for a bit. If every subgroup of Z is of the form nz for n equals 0, blah blah blah. Okay. Okay, I'll leave this as a challenge for you at home. Okay, so now we come into the concrete stuff, a little bit more concreteness that you can start to see things shaping up, especially if you are coming from physics or quantum computing. Certainly, this is already starting to become familiar, right? Yeah, I seem so. Okay, so we define the set of 2x1 matrices with entries in C as this thing here. So we call it C2 times 1, which takes entries alpha and beta, which are elements of C. Now, by convention, in standard convention, in textbooks and these things, instead of writing this, we always write this, which mistakes it with as Cartesian product. But it's not a big problem because we can show, even you, with the concept of isomorphism, you can show that obviously the Cartesian product is isomorphic, set theoretically isomorphic to this. So it doesn't matter. We can use this notation or use the other one. It's just a matter of convenience. And even more, if you add an algebraic structure or whatever topological structure and these things, it's just you will prove the same. It's just one is easier to work. Say for example, this is easier to work when you are doing algebra, whereas the Cartesian product will be much more easier if you are doing things like topology, and these things. So it's just a matter of choice, even though it's like, it's written the same, it's just a matter of choice, which one is more convenient for you. But you can, we lose nothing. It's a bit confusing for newbies, but just to let you know, in our contest, C2 will not be the Cartesian product, but for us, because we are doing algebra, it will be this, okay? Is that understood? Okay, so I believe that's understood. We can define the addition in C, obviously, as naturally, like this. So we have psi1 that takes entries alpha1, beta1, and psi2 that takes entries alpha2, beta2. And then we define psi1 plus psi2 equals alpha1 plus alpha2, and then the second entry is beta1 plus beta2. This is one of the reasons I think we sent an email saying that you need to refresh on, adding complex numbers and these things, because you can see now this operation here inside the matrix is happening in C. So with that, you can obviously easily see this is an additive group, right? Zero element is this matrix 0, 0. The inverse of this is minus, the inverse of psi is this minus psi, which has the entries minus alpha, minus beta, right? Is anyone struggling to see that this is also an additive group? So no one is struggling. Everyone is clear that C2 is an additive group, right? Okay, cool. Thank you. And voila, this is for you, for some of you on the audience, especially the guys coming from quantum computing or even physicists. They will see like spin 1/2 system all over this thing. So I guess you guys, you can recognize this. The physicists and the quantum computing guys, can you recognize these things, right? These are special elements, right? Okay, good. So there you go. Obviously, we cannot do anything with them at the moment because they are not vectors at this stage, because we haven't defined the concept of vector space. Nevertheless, this session, we will do something. We'll try to do something with them using the concept, only group theoretic concept, the concept of left action, having another group acting on the size from the left. That's why, therefore, it's called left action. Okay. I will also do a convention. Sometimes I might break it, especially when I'm working on abstract sets. But when we are working on CN, on additive groups, I will start using psi only for additive groups. So if, like you will see, we will see a multiplicative group. We will not use psi for its element. In that, we will use something else. Okay, so psi will only be reserved for additive groups. Is that clear? Diego, we haven't defined the concept of norm yet. So at the moment, just view these elements as as elements of a group, really, of an additive group. We haven't defined yet the concept of we haven't even defined the concept of a vector space yet. So at the moment, they are just groups. I mean, elements of a group. Okay, because C2 is just a group at this stage. Okay, so I assume it's clear. Let me proceed. By defining this set of 2 by 2 matrices that I write like this, M2 of C, that takes entries in C again. And when you have two matrices, with these entries, A, B, C, D, and another one with the entries E, F, G, H, you define the multiplications like this. I hope those guys who are a little bit advanced, if you see any typo, please let me know. So the multiplication of these guys is defined like this. So if you want to multiply, just follow the rules. If you want to do this nowadays, nobody really hardly you do manual multiplication, because there's so many software like you can do this with NumPy and all other software packages available out there. But nevertheless, good to know if you are doing like a piece of paper. And another important thing, just one thing to note is that I've written this just to make it clear, A times B, but most in test books, when you deal with with the multiplication, you just write AB. So it's like you ignore the times, okay? And you do the same for the thing. So in here, again, as you can see, I didn't write the times. So going forwards, this is how we will do things. We'll try, if I don't write this, if I don't write times, it means there's a multiplication there. It's just we ignored it. Okay. And something to note, something important is that this is not A times B is not always equals to B times A. So in general, you have this thing that we call non-commutativity on these matrices. Okay, and this has a very important consequences, as you will see later, because with the uncertainty principle, as you will see later, when two operators don't commute together, it has deep implications on that. We will get to that when we reach to the quantum operators module of the course. Is it clear? Okay, thank you, Barry. So Amir is asking, is M is I'm not quite sure what. Can you rephrase that again to see if I really understand the question? Is M2 is M extended to? You mean the product? We will get okay. So you mean like for general, in general? Yeah. So this product here is defined at the moment. This is defined for 2x2 matrices only. Yeah. In the future, we will have n by n matrices, square matrices product. The logic will be more or less the same, and you will see also the group that will construct can also be constructed from that. But yes, at the moment, it's just 2x2 matrices. This thing, right? Okay. Okay, so let me. Okay, so it brings, obviously, this is, let me just go back again. This is, you will see this itself, this does not form a group. What we want is a group out of this. This next week, you will see this is a ring. This forms a ring, but it doesn't. Nevertheless, it does have some subsets that can get us a group using this multiplication rule. And that subset is called the GL2C. So it's a set of all, it's a set of all elements of M2 of C that satisfies this. A times D minus BC is different than 0. Those who are a little bit advanced will know that this is the determinant. So these elements are the ones with the non-zero determinants. In other words, these are the set of all invertible matrices. And this is the condition, the minimum necessary condition for a matrix to be invertible. Why we need invertibility? Because we need to make a group. A group, as you saw from the axiom, needs invertible elements, right? So, and the identity of this group is this. So, in other words, for all A in the group, A times I equals I times I equals I, So, and the inverse, a bit of a head scratching. I hope I didn't get it right. You can see this is the, for any element of element A, you have its inverse given by this. Okay, let me check the chat. Yeah, thank you, friend. It stands for general linear group. Okay, So, so if you are giving any A that satisfies this, you can compute its inverse by following this rule here, 1 over this. Then you multiply. I know we haven't defined yet the scalar multiplication, but this is essentially you multiply this with this, with this, with this, with this. That's what. If you do this, you will see that, and then you multiply the result. You will see you should get I at the end. So because it's the inverse of A. Okay. One thing that you should be aware also is that there isn't a standard notation. There are 2 popular notations really. One is this one, but this one is I believe this is the most popular one. This notation here. I use this one certainly. So just be aware. If you see it on the textbook, that's denoted something like this. It means this is the same thing. It's just a different notation. Okay. Okay. So before I move on, is it clear? Does anyone have any questions? So it's clear so far, right? Yeah. Okay. Cool. Thank you. Thank you. Okay, so some of the properties. There you go. Someone was talking about non-commutativity. So yeah, as you can, GL2 of C is generally non-commutative. For example, these, if I was doing the calculations manually, so double check me after, but I believe I got the results right. So if you have this matrix A equals this and B equals that, AB equals this, but BA is something else. So the two are not, AB is not the same as BA. So here's an example of non-commutativity. Another thing very interesting is that this thing contains something we call involutory elements, matrices. Those whose square is as defined in the sense more or less the same as normal numbers, like A times A. In this case, these matrices, their square goes to identities. So in other words, they are the inverses of themselves. So, again, I can see I can imagine those guys in quantum computation and these things, already seeing those examples, right? That they're already familiar with. Is there any, by the way, there's one missing. Which one is missing? Is there something important missing? Which gate is missing there? There you go, H is missing. Don't worry, we will catch H later. It's waiting in the next bus stop. Okay, so yeah, so you can see. Actually, more generally, we will see later, these elements are part of the unitary U2 unitary group, which, as the name suggests, is a subgroup of GL2. And we will work a lot with this in the matrix group section of the course. Okay, before I move on to the next slide, is it clear? Does anyone have any questions, or it's like a piece of cake so far? Very easy. I promise. Yeah, I told you today was going to be very very easy. So no. No. It's not. You will see actually, Nicola. U in general is not an abelian. So. Actually, I could leave that until we get to U when we talk about it, and then you will see the product of the two of them. In fact, you can actually take as a homework, take and try these elements that you see here, because they are part of U. Try to multiply them in different order and see if they show up. You will see that they are not. Then then you have the proof that U of 2 is non-abelian. Okay. Okay, so yeah, Barry is okay. I believe everyone else is also okay. So, okay. So, let's see what we wanted really. So we wanted something. Obviously, C2 is not. Let me before I go through the definition, just to give you what we wanted, right? let me go back again to the slide. So at this stage, you know, C2 is just a group, right? We can't do the manipulations, you know, we can't apply operators to them, right? Because it's just, you know. So that's what essentially that's what we want to do with the left action, you know. So you will see. I will say it now in advance before we go through this, but it's obvious that what we want is to recover from using group theoretic concept to recover the matrix, you know, the matrix operation on size. Okay, that's what we want, you know. So we want to have in this case a square matrix in 2 by 2 matrix acting on a column matrix. That's what we want. But we will only use the group theoretic concept, right? Because we don't have the linear structure yet on C2. Okay, so suppose, by the way, the left action, the concept of action can be defined on abstract groups. So it's not just GLH2. I'm just doing this because today I want to be very easy, not to work in abstraction. But this concept can be defined on, it's actually defined on abstract groups. So it doesn't have to be this concrete group, but I'm doing it because, you know, it gives, it's a little bit, it makes things a little bit more clear for most of you who are new to these things. Okay, so, and another thing, it can apply to sets that are not necessarily groups. So it can be a set. Obviously, for our purposes, we want X to be the C2, which is at the moment has a group structure. So a left action is on a set, on a non-empty set, obviously, denoted dot at this stage. Don't mistake this with the other concept of a dot product. Okay, it's not the same thing. It takes an element of GL2 and a psi and produces another element that we call that we call A dot psi, which is also an element of X. And it has these properties. So, you know, if you take B psi, B dot psi, and then you apply A is the same as, you know, AB, and then taking psi for all AB in GL and for all psi in X. And of course, the identity times dot psi equals psi for all psi. Okay, let's see. Okay, so Amir, you have a question on the previous slide. When you mentioned U is a subset of GL. It's my confusion. I'm just okay. So let me go back again to the slide just to help our friend Amir. Okay, where is it? Okay, I shouldn't really have mentioned this. The thing I'm just giving you because, you know, today is a lecture on groups to say, you know, it is a subgroup, of course. You know, I'm just calling it a subset because it's obviously to be a subgroup. It has to be a subset, right? So, but we don't know yet what, you know, how is this defined? That's why I don't want to go through, you know, the detail of defining what a unitary group is, but I'm just saying it's a subgroup because, you know, we are dealing with its parent group, right? So that's why I'm mentioning this. It is a subset. U of 2 it is a subset of GL2. Is that clear? Okay, maybe at the end I will come back to this again in the Q&A so I can clarify this if that's okay. You mentioned at the top of the page, well, okay, we'll come back to this. Okay, so so Amir, you are saying, yeah, yeah, so I'm defining it. Okay, so here I'm saying, it's the set and this thing, just to say, what to give the property that its elements have to obey. In this case, they have to. They are elements of the M2 of C, but they have to obey this condition. And what I'm saying is that this set is a group under the multiplication that we already defined previously in M2 of C. Is that clear now? Okay. Okay, so let's go back to where we were. Yeah, so left action. So we have the general linear group acting from the left on this set. And I claim that, this is true. If you have this thing, if you think a bit, going through the definitions and looking at the properties of the multiplication that we define for A, and mixing it up with this definition, you will be able to prove this. Okay. In fact, in the matrix group section, we will give a general proof of this for any group. So that's why I'm not bothering to go through walking you through a proof of this. But this is true. It's something I believe you can prove also. Okay. So this is abstract now. Let's see a concrete example of this in play. Okay. So if we have A in this form in GL2 of C, and then we have psi in C2, then we can define the dot product as the normal matrix multiplication that you all know, okay, which is this thing. I hope I didn't have any typo. If I did, let me know. But this is, so essentially, for those who already know how to multiply 2 by 2 matrices with a column matrix, so the definition of this thing is the same as that. And obviously, because of that, we can verify, for example, here that if you have this what we call before X gate, thanks to our friends in quantum computing, this X gate matrix, and you do the left action of it on this psi, you will get this, right? So the quantum computing guys will definitely know this. They will already seen this. Okay. Yes, thank you, George. Yes. Okay, so is it clear now what's left action? So what this group acting on the left on C2 is? So essentially, what we did was to recover the normal, 2 by 2 matrix multiplication to a column matrix. I won't call it a vector because psi is not a vector yet, but you know what I mean. Yeah. So okay. Is it clear? Does anyone have any questions on this? On the left action? Obviously, some of you might be thinking, what about right action? Yes, there is also. You can also define the thing from the right to left, but we won't do that here. We will do that in the general in the matrix group section. So this is it. So from a formal point of view, the matrix multiplication that this is the thing, how powerful abstraction is, right? We didn't even need to go through all this linear algebra stuff to recover this the product of a 2 by 2 matrix with a column matrix, right? So there you go. So now I have a left action challenge for you guys. Here's someone was saying our friend H was missing. Here's our friend H. So what I want you to do as a home challenge for those of you who bother, those of you who are already coming from quantum computing or physics background, you must have done this, zillions of times, because these are the Pauli matrices, right? If you are working on spin 1/2, you already seen these things, right? Correct? You have already done this. Yes, the operator have to be from the general linear group. Yes, yes, yes. If you don't want to use this, but I'm saying all this, you can use other operators that provided they are in here also if you want. But just by applying this, I guess for those of you already coming from quantum computing, you already done this zillions of times, so you probably want new operators, right? I think that's what Aditya was asking. So yeah, so as an exercise, maybe you can find other elements, other interesting elements of this that you can apply to the size. But bear in mind, they might not be unitary. Yeah, so that's something that you have to bear in mind. Whereas these ones are unitary because obviously we did. I'm telling you now. You also know that they are unitary. But we haven't defined yet the concept of unitary. We will do that in the future lecture. But just bear in mind that not every element, of GL2 is unitary. It's a massive. It's a big group. So, okay. Okay. Is there any other questions? Is there anyone lost on something or didn't understand something? Before I move on to the next part, the next section. Okay, clear so far. Okay, thank you. Okay, so this is something that I wasn't planning to add, but now that we are here, I was like, why not add it? So this is not the commutator that everyone is, used to. The Heisenberg commutator. For those of you coming from physics background. That commutator, will get closer to it next week when we define the concept of a ring. For now, this is the group commutator. So, and this is actually another general concept that it's not just defined on GL2, it can be defined on other groups, okay? I'm just doing it because obviously we are working on this to be more concrete, okay? So, given two elements, A, B in GL2, we define the commutator as this. So this bracket where we put A and B, and then there is we compute it as follow. You take the inverse of A, which you know how to calculate. You multiply it with the inverse of B, which you also know, and then you multiply the result with the result of the AB. Okay, so this is it. This is all you do. Just take the inverse of A, multiply with the inverse of B, and multiply the result of that with, okay. So here's something for you, for you to scratch your head. In the future lecture, when we're talking more in general groups, we will prove this. It will be nice for you to prove that this is true, that, for example, the commutator of AB equals the identity only if A and B commute. Remember the definition of A and B commuting, meaning that AB equals BA, okay? And then you have other identities here, okay? Let me check the chat just to make sure. Does anyone have any questions about the commutator? It's at least the way of calculating. I mean, when we get to the quantum operator section in this will be much more funnier, right? Because we'll have proper operators that physicists use and these things as to play around with. Okay, but for now we are not there yet. So yeah. Okay. So as a homework, go and scratch your head around to prove this and prove this and prove this. Okay. And I also have an extra homework for you, which is this. So I want you to randomly calculate the commutators between these operators and then apply the result of the commutation to these elements and see what you get. You might not get anything, but yeah, just as a way of playing around and getting used to these things. Especially for those who are new to this, it's very important to practice, really. So part of practicing sometimes is doing things that maybe will not yield anything interesting, but nevertheless you are practicing. So as an extra challenge, I call it the extra commutator challenge. For those of you who want, you can do this. By the way, just the significance of the commutator in physics, you will see that later with the thing. In fact, you can Google it to say the uncertainty principle when two commutators, two operators don't commute. For example, mathematically, you will see that loosely speaking, two operators that don't commute cannot share eigenvalues. So I believe physicists can correct me on this, on the audience. The interpretation, loosely speaking, they give to that is that these two operators cannot be measured at the same time because they don't share that, they cannot share common eigenvalues, for instance, loosely speaking. We will have a more precise definition of this after when we reach the. Yeah, so the commutator also mathematically measures the, yeah. So that's a good point you made, George. So a group, an abelian, so an abelian group, so a group is abelian if only if AB equals I for all of its elements, So it measures the commutativity of the how abelian, if you will, the group is really. So so Diego, did you find anything interesting? You already done the commutator of something? Okay. Okay, yeah, that's fine. We can, as I said, it's yeah, that's not a problem. It's okay. You can share it after if you want, especially when we have this Slack channel. Hopefully next week I will be able to update you. I haven't had heard back yet from my colleague about what's the terms and these things, but yeah, I hopefully it's helpful. It's interesting. You can go and play around with it. This is not the commutator that the other commutator that physics, most in physics are thinking about, but nevertheless is also an interesting commutator, right? So yeah, Diego is very fast calculating. Yeah, so maybe if you want, Diego, at some point, if you want to share your result, I'm more than happy to pull you, and you can say share with the audience. What did you find with this group commutators? So okay, so there's no question, I guess, on the commutator. It's very clear how to calculate it, and the challenge is, you guys go and play around with it and see, especially those guys in quantum computing, and maybe you can find, play around with the concept of commutator and see if you can find something interesting, So yeah, because the quantum gates, the unitary gates are groups, so they are and we already seen that they are a subgroup of GL2. So okay, so. This was a very short, as you can see, not much was covered, and that was deliberate because it's the first section of abstract algebra, and I didn't want to hit you all like with too much of a thing to lose people. But nevertheless, I hope it was very interesting, and this style of connecting it with the stuff with our goals, especially with the quantum stuff, was useful. So that's why I avoided, the classical approach of, doing the intro into a kind of a pure group theoretic thing, but rather by thinking on the application side. So there are a lot of things that were left, like the concept of group homomorphism and blah, 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 all these things, but it's not a problem. For those of you who don't know, we will come back to this. That's why I added an extra lecture on this when we go back to the matrix groups. we'll cover these concepts and other concepts that you need. So yeah, before I share the lecture material, I mean the study materials, the comment I make on them, does anyone have any questions so far? Yeah, it's possible, Diego. If you did the calculations, I trust you. Yes, I can. Okay, so you want to use the slides like my slide, the presenter's slide to take notes and these things. I can try to do that 1 hour before or something. Yeah. The only tricky part is sometimes sometimes like I might do like a lastminute.com type of changes, and then the slide I give you is not the same as. But it's not. Yeah, I can try to do that next week. Yeah, upload it before and. Maybe you can follow the, I don't know, you are following the repository, the GitHub repository. Maybe you can see the notification when I upload something, and you can, yeah, I will try to do that. Okay. And the other question is the theoretical part. Can we check the, yeah, it's true. Yeah, maybe with the Slack, this will only be feasible with Slack. Yeah. Yeah. And then you can, form maybe a study groups and these things, you can also find references. Yeah. So, yeah. Yeah, hopefully I will hear about Slack. Then you can, and also for those of you who want to like submit group work or something, you can start interacting with each other and, helping each other. Maybe some concepts are easier to observe by some of you than the others and vice versa. So, yeah. Okay, so there's no question about the theory side so far. So the lecture notes will be, for those of you who are new, so the way it works, the study materials, we, instead of us going through the hassle of producing everything, like reinventing the wheel, we kind of curate from, available sources that are out there, well written, and that we think, could help you assimilate not just the concept that we cover, but the extra stuff that we don't cover. And in this case, we found this, my colleague, when he shared this, I think it's very nice notes by Professor Jim Howie. You will, by the way, just a disclaimer, this is not an endorsement of Professor Jim to this series. It just happened to, his lecture, publicly available lecture notes are very interesting. So, we thank him for that. So the pages that you should really focus on is from pages 3 to 25. You will have some of the stuff that I mentioned that I didn't touch are contained in there. So if you can wrap your heads around that, that will be great. If not, if you have difficult, that's not okay. That's fine. You will have the opportunity later to revise again when we give the extra lecture on group theory. And then this is extra bonus really for those who really want to. If you can go like at least from page 27 to 44, that will be even cooler, but you don't have to. So yeah, so this is all I have to share. And another thing is, don't forget these the slides and the curated material from Professor Howie will be available on this repository. And the recording of this session will also be available later on YouTube. And then obviously you can follow us on Twitter, blah, 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 and hopefully Slack. Once I find out, I will send invites for people to join. So yeah, so that's it really. I will stop sharing the slides and put the Q&A. If people have questions, you can put it there. If not, if you don't have any questions, everything has been clear, then Gitter, okay. Yeah, I can, I'll speak to my could see if we can connect with the Gitter. The question is whether the rest of the audience will take. I mean, for yeah, thank you. No problem, Francesco. It's a pleasure, and I hope it was useful. Anyway, it's just a start. This is just a second session, and things will become harder as we go along, right? But hopefully, this approach of distilled. Distilling things into small chunks as opposed to hitting you in the head with stuff will be very very helpful. So yeah, does anyone have any questions on the poll? If you don't, one thing I want to comment on the thing. This invites for the next session. So if you register, for those of you who have registered for this lecture, for instance, we will send you. We will send you the link for you to register yourself, so you don't need to fill the Google forms. Okay, the Google form is normally just for those who already the new people coming in from the newsletter. But for you, I will send. So check out for the Zyko group email. It will have the password and these things for you to register. It will be a secret URL with a password, so you can register yourself as opposed to us registering you. So yeah, if you have any problem anyway, you can still fill out the Google. I will add you manually and this thing, but you don't. You can after the session, we will send you, once we create the page for the next lecture, we will send you the password and the secret URL for you to log in, register yourself. So you don't have to do the Google form stuff. That's only for those who haven't been verified yet, like new people. We want to make sure that they're not being spammed. So yeah. Okay, so I assume there's no more questions. If that's the case, then yeah, we catch up next week where we will talk about rings and fields, and we are getting closer to talking about vector spaces and these things. So yeah, so have a good weekend, and thank you so much for tuning in. And yeah. I'll see you.